To estimate failure in this case, we can use this curve. There are few methods that can be applied, and if we plot sigma alternating versus sigma mid-range, we can have an idea of the safe zone of this machine element. So for example, when the alternating component is 0, this if sigma A is 0, that means we only have static stress, which is a mid-range. That means if there is no alternating from the mid-range, that means we have static components only. Static component, that means we can go up to yield strength without failure. We can only expect failure if we exceed yield strength and approach ultimate strength. Ultimate strength lead to complete failure. Once alternating component is increased, then we will have fatigue or dynamic condition. So in this case, if alternating component is maximum value when mid-range is 0, that means we have completely reversed. And for completely reversed, the limit is endurance limit. Okay, so starting from these points, we have few methods that can be applied. Modified Goodman is a most used one, or the simplest method to use. Modified Goodman, we link endurance strength with ultimate strength. So the mid-range stress is compared to ultimate strength, and alternating stress is compared with endurance limit. Okay. For static situations, we use yield line or Langer line, which uses yield strength for both mid-range and alternating. So that's why it is called check for yielding or the yield line. And then we have some other fatigue criteria also. There is a Gerber line, okay, and there is the elliptic line, ASME, and there is the Cederberg line. So the Cederberg line here is the most conservative. The safe zone is always under the curve. So according to Cederberg, only points under this curve are safe and no failure is expected. If the combination of mid-range and alternating stress, let's say your mid-range stress is this value and your alternating stress is this value. So this is your point here. So your point is safe according to Cederberg, it is safe according to the elliptic line, it's safe according to Modified Goodman, to Gerber, and the check for yielding also is safe. If the point is, let's say, here, the mid-range and the alternating stresses give you a point that is here. So this point is safe according to this curve, which is the elliptic, and to this curve, which is Gerber, but according to Cederberg and to Modified Goodman, this is not safe and failure is expected. Okay, if the point is outside the yield line, if the point is not under the curve of the yield line, that means we will have failure from first cycle. There will not be there will be static failure. Okay, so here we have a load line or a slope for a point that is here. For any point, it will give you the safety factor for that point. Okay, you connect your point with a 0 and you can solve and estimate the life. Okay, so all these criteria can be used if you are asked to choose a conservative check. Then Cederberg, which is this line, gives the smallest area under the curve, and it is the most conservative check. Always also check for yielding using this line, and modified Goodman, of course, as it's said here, simple check, simple to use, and it's more conservative than Gerber, but it is widely used to check for fatigue failure. So here you have the equations. For Cederberg, we use endurance limit with alternating stress and yield strength with mid-range. For modified Goodman, we use endurance limit and ultimate strength. Okay. Here the fatigue factor of safety for intersecting equations and for the load line. A summary also for all the equations for Gerber criteria. This is the ASME-Elliptic. Okay, and here we have an example for a material, cauldron material. Diameter is given, and we have fluctuating tensile load, so varying from 0 to 70. So this is not completely reversed. This is repeated load. A repeated load leads to repeated stress. Okay, because the ends have an and then we have fatigue, stress concentration. So the value for Kf is given. You don't need to calculate fatigue stress concentration factor. Value is given. You just multiply this number 1.85 with your stress. In this problem, first you need to find ultimate strength for this material, which is given in table A20, and then you need to calculate endurance limit. Start by 0.5 of this value and then add all the factors. These three factors come from material and type of load. Axial load. Tensile load means our load is axial. This is not bending, this is not shear. So Ka is a surface factor for cauldron material, and Kb is for axial loading is 1, Kc for axial loading is 0.85, and then there's no mention for temperature and reliability. You can calculate your endurance limit. Then calculate both alternating and mid-range stresses. You need to add stress concentration for both alternating and mid-range, and then use one of the failure criteria to calculate factor of safety. Okay, so for this example, your point was here, alternating and mid-range, and the load line is this load line. Okay, so in this curve, we have Gerber fatigue curve, and we have Langer line or check for yielding. Okay, so it will cross Gerber line here, and it will cross yield line here. So the point is safe because the value here is less than what is given here. It is within the safe zone. So this material will not fail because of variable loading, and it will also not fail because of the static loading according to the yielding